Lesson 6, Chapter 1, Scientific Notation. This is a concept I'm sure you're familiar with, but let's review a little bit. Scientific notation is when we write a number as a product and an integer of a power of 10. The number needs to be greater than or equal to 1 and less than 10. So anything basically between 1 and 9 point something. Okay? Example number 1. First thing we need to do is we need to understand the difference between standard form and scientific notation. This is what scientific notation looks like, and just the numbers the way that you've been writing them pretty much all your life since elementary school is standard form. So in this case we're going to change this from 5 and 34/100ths times 10 to the 4th to a standard form number. And the way to do that is to simply move the decimal point either right or left in all of these, and I'm going to talk about that in a minute. In this case, write out the number 534. So we've got 534, and because this is a positive number, I'm going to add some zeros here. I would recommend that you just put some zeros on there. It doesn't matter how many to start out with, and see how it works. And because it's a large number, we're going to move the decimal point to the right. We'll talk more about that in the next slide. So we started here, right here, and we're going to move the decimal point 1, 2, 3, 4 spots. So that's going to put the decimal point right there. If we count back 3 to right here, that's where our comma is going to go. So we have 53,400. So here's your answer, 53,400. Now let's take a look at another one. Example 2. You have 3 and 27/100ths times 10 to the negative 3. So in this case, because it's negative, we're looking for a small number, so we're going to move the decimal point to the left. So again, write your digits out, 327, put some zeros out front, and we're going to start right here because that's where the decimal point was, and we're going to move 1, 2, 3 positions to the left. And then we're going to put the decimal point there. Always put a 0 out in front of it to call attention to the decimal point. 0.00327 is your answer. Please do letters A through C. Okay, example number 3. Now we're going to take a standard form number, 3,725,000, and write it in scientific notation. Now remember, this number and this number are the same number. It's just a matter of the form you write them in. Okay, so we've got greater than or equal to 1 but less than 10. So in other words, 3.7 is the obvious choice. I could put a decimal point here in 37 and use 37.25 times 10 to the 5th in this case. It would be the same number, but it would be improper. We need to have the decimal point here so that we have a number between 1 and 9, including 1. So in this case, we have 3.725. So you write 3.725. We use all digits that are non-zero. If there was another number here, we would have to go to that number. Once we have nothing but zeros, we no longer need any more digits. 3.725 times 10 to the some power. So let's figure out what that power would be. The decimal point was right here, and we moved 1, 2, 3, 4, 5, 6 spots. Now this is what I was talking about on the previous slide. Don't think too much about left or right, because in this case, because it's a negative number, we're going to move to the left. This is telling us which direction to move. But in this case, if you always think about left and right when you're doing scientific notation, you're going to probably get tripped up sooner or later. A better way to think about it is it's not about left or right, it's about big or small. Okay? So in this case, you see a negative exponent? You should think that it's going to be a small number, therefore we're going to look at decimals with the decimal out in front of the digits. In this case, obviously this is a big number. Definitely, even though we moved left, don't think negative 6. It's to the positive 6. Think of 10 to the 6th. 10 to the 6th is with 6 zeros. I got enough there? That's times a million. That's 3.725 million. Which really, if you look at this, we should see that that's 3,725,000. That makes sense. It's a very large number. Next we have example 4. 0.000316. Write down the 3.16 because we know we're going to need a decimal point right there. And now we just need to figure out how many places did we move. We moved 1, 2, 3, 4, and that obviously is a small number, so it's 3.16 times 10 to the negative 4. Please press pause and do letters D through F. Example number 5. In this case, we're asked to take this data and order the numbers from greatest to least. This is probably the biggest thing to worry about with these problems because they should be really easy. Kids tend to trip up because they'll ask you greatest to least in one case, and then they'll ask you least to greatest in the next case and trip you up because of that. How do we order these numbers? Well, it should be pretty simple. If you think about the number 10 to the 7th versus 10 to the 6th, we're taking a number, and every one of these are going to have a single digit here and then the decimal point. That's the idea of scientific notation. So if we multiply it by 10 to the 7th, that's multiplying it by 10 million. If we multiply it by 10 to the 6th, that's multiplying it by 1 million. So obviously these numbers are going to be smaller. 10 to the 6th is smaller than 10 to the 7th. 10 to the 11th would be even greater up here. 10 to the 3rd would be even less down here. So once you have those in groups where you have these two are 10 to the 7th, these two are 10 to the 6th, then it's a matter of taking a look at it. It's 1 and 6 100ths versus 1 and 3 100ths. Obviously 6 100ths is greater than 3 100ths. And then we move down to the next one, and 7.15 or 7 and 15 100ths is greater than 1 and any amount of hundredths. So compare it digit by digit. If you need more help with that, see me and I will instruct further, but I believe that we have a pretty good concept of that. So there's how we put them in order from greatest to least. United Kingdom, Canada, Mexico, India. Please press pause and do letter G. Example number 6. 2 meters per second is the speed that we're looking at, and they're asking you, should we report that as 1.92 times 10 to the 8 seconds to get to the moon, or should we say that it would be 6.09 years? And which of those should we use, and why should we use that particular one? And in this case, we're definitely going to use 6.09, 6 and 9 100ths years to get to the moon. And why is that? First of all, it just makes common sense, which is what I'm sure a lot of you are thinking. But some of these will get a little bit more tricky, so apply a rule. And basically the rule is simple. If we're talking about a very large distance, a very large number, a very large measurement, whatever it is, then we are going to use large units to represent it. And years are definitely much larger than seconds. So that's what we're going to use here. Please press pause and do letter H. These are the solutions to 1-6 letter problems. First of all, letter A, we have 7 and 42 100ths times 10 to the 5th. Scientific notation, we're being asked to turn it into standard. So we should take 742, large number, so we're going to add some zeros, see how many we need. Then we're going to move the decimal point, big number, we have to move it to the right, and we're going to move it 5 spaces. 1, 2, 3, 4, 5, so we don't need that 0 there. So we should have 1, 2, 3, comma here, 742,000 with the 3 zeros behind it, 742,000. Letter B. In this case, we have 6.1 times 10 to the negative 2. We're talking small number here. So we're going to have the 6 and the 1, the 2 digits we had, and we're going to put some zeros out front, and we're going to move 2 spaces. The only way we can get this number smaller is by moving left. So we move 1, 2, that would put the decimal point right there. We should have 0.061 or 61 1,000ths. Letter C, 3.714 times 10 squared. So we have 3714, large number. We're going to move 2 spaces. We started right here, 1, 2, and it's going to end up here. Notice that we don't end up with any extra zeros here. So we just moved it 2 places. We're going to have 371 4/10. Letter D, we have 14,140,000. And we're going to obviously put the decimal point right there. So we're going to have 1.414, the rest is zeros, we can ignore them, 1.414 times 10 to the something power. And how do we figure that out? It is big, so is it going to be positive or negative? It's going to be a positive number. And how many? 1, 2, 3, 4, 5, 6. Right there's where we're going to need it. 7. So it is 1.414 times 10 to the 7th power. Letter E. We have 0.00876. Right here is where the decimal needs to be. Gives us a number between 1 and 9. So we have 8.76 times 10. Is it going to be positive or negative? Small number, it's going to be negative. How many places did we move? We moved 1, 2, 3 times 10 to the negative 3. Letter F. Right here's where our decimal point is. We only need to move it that little bit to right there. So it's going to be 1.14 times 10 to the what power? Well, is this bigger, small number? Small number. So it is to the negative first. We'll move just one spot. Letter G. Here's another one of those problems, but in this case they ask order them least to greatest. So we're going to look for the smallest numbers. So the smallest numbers are obviously going to be the 2 that are 10 to the 5th power versus the 2 that are 10 to the 6th power. Because 10 to the 5th power obviously is smaller than 10 to the 6th. 10 to the 6th would have 6 zeros, and 10 to the 5th would have 5 zeros. And 7.21 or 7 and 21 100ths is smaller than 9 and 1 100th. So that's the way we order these two. And 1 and 3 tenths is smaller than 2 and 2 tenths. So that's how we order these two. Remember to focus on this first and then focus on this second. So your answer should be Boston, then Metro DC, then Las Vegas, and then Los Angeles. Letter H. The seafloor moved 475 kilometers over 65 million years. It moved, in other words, 7 and 31 hundredths times 10 to the negative 5th kilometers per year. Or you could say that it moves 7 and 31 100ths centimeters per year. So the question is, which of those should we use? And the key thing to focus on here is that is a small amount of movement. That's only centimeters per year. So just imagine sitting around waiting to watch something that moved 7 centimeters, about probably that far, in an entire year. That's a very small movement, even though we're talking about over many, many years. That's a fairly large distance. That is a very small rate. That's why I put the rate here. So since it's small, we're going to use the smaller of the two units. Now some of you would look at the year and say, well, year is a pretty large unit. But we're not focused on year here. We're focused on either centimeters per year versus kilometers per year. Okay, so clearly we should use a small unit, so we should use this one here, 7.31 centimeters per year. If you think about this number here, we would have to have all those zeros in there, 7 kilometers per year. That would be very difficult to relate to, whereas we can relate to 7 centimeters in a year fairly quickly. Thank you.